Oh, you let us know. Here we go. All right. Good evening, everyone. Thank you for joining us. We're approaching the end of Data Week. We've had a bunch of lectures in SAS and in R, and we're super lucky tonight because you'll be learning some machine learning in R. Arjun volunteered to do this, and I'm super glad he did. I'm excited to learn from him. I've shared the link in the chat box for the OneDrive folder with the materials. There's 3 documents in there for you to download to be able to follow along with today's lecture. I'm also putting in the chat box the link to the attendance. We are raffling off an iPad, a Garmin watch, and wireless earbuds. For each lecture you attend, you get entered once into the raffle. And so don't forget to fill out the attendance before you leave tonight. And then all of the lectures from Data Week are being recorded. And so we'll be posting those on the CETA YouTube channel probably sometime next week. But to get access to those, follow us on LinkedIn or Twitter, and you'll be able to view, see a post once we make everything go live. But I will hand it over. Thank you so much for being here, and have fun learning machine learning.
Hey, hello. Thanks a lot for the invitation. I'm very happy to be here. Hey, everyone. It's amazing that a bunch of you showed up 5:30 in the evening on a Thursday to do learn about some machine learning. My name is Arjun Krishnan, and I'm an associate professor here at CE Arjun. I got here just less than 6 months ago. And what my goal is to sort of introduce the very basic ideas of machine learning, and then take you through a hands-on worked out example of how to apply machine learning to a data set. Okay, so that's the goal today. Intro to ML, and then building a predictive model from the beginning to end using gene expression data, right? I would be very grateful if something that I'm saying is not clear and you will interrupt me in the middle, okay? So that we can chat and then I can clear things off. I'm also going to be juggling a little bit between my iPad and the screen here, so please bear with me if there are small stalls. All right. Okay, so hopefully what I'm going to do first is to switch over to my my tablet, and then share my screen there so that I can draw stuff. But in the meantime, what you can also do as you follow along what I'm teaching is to make sure that you download the files and keep them ready, open RStudio. And one thing that I will say perhaps, so let me just do this once more. If you open RStudio, I'm assuming you can still see my screen. Right. Please open this particular markdown document that I showed you. And then the thing that you need to do your hands-on exercise is to install 3 packages, okay? Tidyverse, tidymodels, and glmnet, okay? Only if you install those 3 things, you'll be able to load these libraries and work along with me, okay? Can folks give me a thumbs up or thumbs down, whether that was clear? Okay, how about the participants? Okay. So you will have time to install because I'm going to talk about concepts for a while. So now is a very good time to download, start installing the packages so that you have some time, okay? All right, so let me switch over to my tablet. All right. So what I want to do is to begin with this basic idea of machine learning, right? And typically in machine learning, what you would have heard many times is to basically say that you will take a data set and then try to make predictions about something. But what I want to do is to begin with this idea called unsupervised learning, and then use that to pivot towards, predicting something about the future. So let's imagine, typically, all the data that we get, that data can be text, it can be numbers, it can be images, or whatever, we can almost always arrange them in a rectangular block like this, okay? Like what I'm showing you here, where all the individual samples are along the rows, and everything that we can measure about them, which I'm going to call features, are along the columns, okay? So for instance, you can think of every single row as a house, and then every column is something that you can record about an individual house. It can be the area, location, the distance to the nearest mall, school district, the average population, and anything that you can measure. All those are called features. And then you record this about every single house. So every single row here is a single house. And then every single column here is some attribute about the house. So therefore, samples along the rows and features along the columns. All right. Okay. Now, one of the things that we can immediately do when we are given a data set like this is to explore this data and find patterns in this data without any other external information. And this is typically achieved by employing tools or approaches from unsupervised learning, right? And the three major things that people do in unsupervised learning is, one, to do clustering, which is to take the rows and then group them into tight groups if they have very similar values across all the features. So this is like finding groups of houses that have very similar properties, right? If the individual samples were people and the columns were about various attributes about people, then you would be clustering people. Or it can be different items, or it can be different movies, and you'll be clustering them, based on anything that you measure about these movies and so on. Right? Now, the second thing that people do in unsupervised learning is called dimensionality reduction. Dimensionality reduction. This becomes very important because typically in this big data era, when we can easily measure large number of features about individual samples, what happens is that let's say we have n samples and p features. Typically, p is way larger than n, which means that we can, let's say there are 100 houses, we can measure so many things about each one of these houses that the number of parameters, the features that we measure, is way more than the number of houses that we begin with, right? The same is true for genetics or molecular data. For instance, many of you might know about this technology called gene expression profiling, where you can take a biological sample and measure the activity of all the genes in the genome in one shot. So in that case, typically what happens is that we might end up with tens or a few hundred samples, but from each sample, you're measuring 25,000 or 30,000 genes. The same goes for genome-wide association studies too, where you can take an individual and measure the mutation across the whole genome. So therefore, you have millions of features for every single individual. Dimensionality reduction is essentially the idea that you can take this large data set that is extremely wide and really short and reduce the number of dimensions of the features so that you can still represent all these samples in a much smaller dimensional space. So for example, principal component analysis is something that's very common. The third is called outlier detection. Okay? Outlier detection. All right. Outlier detection is this idea that you can take this data set and then ask, based on the overall distribution of the features across all these samples, are there a small number of samples that stick out? Right? So this is how, for example, banks detect credit card fraud. So they are not looking for overall patterns in the data, but they are instead saying, is any particular credit card transaction based on all the things that I measure about this transaction somehow standing out based on the distribution for all the other transactions? And if it's standing out, it's an outlier. So something suspicious might be going on. Okay. All right. Are we at an intuitive level? Are we good so far? Can folks give me a thumbs up? If
Looks good. No questions in the chat.
All right. Okay. So this is unsupervised learning, again, where you take the data within this data set, within this rectangle, and find patterns in this. Supervised learning is taking it one step further, where you not only have the data set of samples by features, right? But we also have something called a target or an outcome, okay, which is this vector here. Let's go back to this original example that I talked about. Let's say the samples are all houses, and then the columns are all various things you can measure about the house. A target variable can be how much this house will sell in the market today, right? So if you collect enough data, you will have a large number of houses, various features, and the cost at which that house sold, let's say in some recent history, let's say in the past 6 months. This is a data set which is really amenable to what is called supervised learning, where you can take the matrix on the left and try to use the data to predict the target outcome on the right, which is to use the features of the house to predict the selling price of the house. For molecular data, for example, every single row here, let's say, can be a biological sample, and then the values along the row can be the expression level of every single gene in the genome in that particular sample. And the target variable could be which tissue did this particular sample come from, all right? So it can be brain, adipose tissue, heart, liver, and so on. Those are the ones that could be entered in the target outcome. So now the question is, can you somehow use these values along the row and build a model to predict the target or the outcome? Okay, this is essentially supervised learning, all right? I'm going to refer to this matrix as the X feature matrix, this whole matrix on the left. And then this is the target variable. And this is usually referred to as Y. All right. So what we ultimately want is to somehow predict Y as a function of X. Somehow use X to predict Y. Okay. This is what we are trying to achieve in supervised learning. All right. Now, here is a question for you. I would like some of you to either type this in the chat or tell me something about what you think. Again, this box, let's say, represents all our data. Let's say we have a few thousand samples, biological samples. We have measured, let's say, 20,000 activity of 20,000 genes in each of those samples. Again, remember that every single row here is a biological sample and the activity of all the genes in that sample. Okay. And then I have recorded which tissue that sample came from. And I want to build a model that does the following. Given the gene expression profile of this particular sample, can you predict which tissue in the body it came from? Okay, that's the question I want to solve. So this is, let's say, tissue. Okay. The gene features, the biological samples, and then the tissue. All right. So in this case, if I do want to build a model, how do I figure out, if I use all this data and want to build a model, how do I figure out how good the model is? Any ideas?
I think one thing I'm kind of thinking of doing for my research was to something like k-fold cross validation, or splitting the data into testing and training, where you use one or some of the samples, the majority of the samples, to generate your model, and then you test that model and something else.
Exactly, right? So if we have a large number of samples, what we can do to figure out how good any model that we build is to basically take this data and then split this into a bunch of groups, right? So for instance, what we're going to do is to, let's say, completely split this data into two halves, right? And you can call this, I'm going to use this model, use this part of the data to train my machine learning model, and then use this part of the data to take the model that I just trained, apply this on the remaining data to basically figure out how well we did. That is because once you train a model, when you apply it to the test set, we already know what the true tissue for each of the samples in the test set is. So we can compare it to what the model predicted, compare it to the ground truth, and then see how good the model is. Okay. Now, this splitting is not that straightforward, okay? Because one of the things in machine learning models is that there are going to be many parameters and especially hyperparameters. I'm going to talk about what that is in a second. You can think of this as knobs and switches that you can sort of tune to change a little bit about the underlying model, right? So what we need to do is to not only just train a single model, but to train a bunch of different models with slightly different model settings. But if you keep changing this around, you can't take each of those models and then you need to figure out which model setting is the best, and then figure out the best model setting, and then apply that finally to the test data. So therefore, to figure out which model setting is best, we need another split of the data set. So therefore, we need to take our data set and to do 3 splits. So let me just say, let's do it this way, right? I am going to do 3 splits this data. So in this case, what we're going to do is to split this into 3, use this first part to train a machine learning model and try many different model settings, and take each of those model settings and then apply this to the second split, which I'm going to call the validation set. Keep applying to the second set, figure out how well the model is performing on the validation set, and figure out the best model setting. Once you have found the best model setting, take that best model and then finally apply it to the test set, which will give you a final really good sense of how good the model is. All right. So we are going, even in practice, what we're going to do is to take the whole data set, whole data, take a chunk of it, leave it as test, and then whatever is left, the other one, we're going to split that into training and then validation. All right. So these are the splits that we're going to do.
Can I ask you a question?
Yes.
What proportion of the main data set goes into each of these?
Fantastic. So now that itself is something that you can tune a little bit, but typically what a really good starting point to do is to say that I'm going to take my whole data set, keep 20% for testing, another 20%, let's say for validation, and use the remaining for training. In the example that I'm going to work out, you will see that splits are slightly different, but roughly around this ballpark. And this is one way of doing, model evaluation, doing data splitting for model evaluation, but there are more sophisticated methods, but I'm going to keep this simple for this particular workshop. All right. Now, I have, up to this point, I've told you that there is a data set, there is a feature matrix, target variable, and we're going to split this data and somehow build models at various stages and figure out how good these models are. But what do I mean by a model, right? So I'm going to talk about that by explaining a very simple machine learning model. So now, remember I told you that this matrix is called X. Every single column here is a single feature, right? And I'm going to refer to them as X1, X2, and so on until XP. There are P features, right? And every row here is one sample, right? These are samples. These are biological samples. X1, you can imagine that X1, X2, X3 are different genes in the genome. And the value here is the expression level of gene 2 in this particular sample, right? Now we have our target variable Y, which tells us which tissue the sample came from, right? Now, a really simple model to predict y from x is a linear model. So a linear model says, I'm going to somehow predict y as a linear combination of every single x value, x1 plus beta 2, x2, dot, 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 beta. Okay. Now, do you all hopefully see that this is very similar to fitting a line? Just that there are many different coefficients here, because you might have seen things like, C plus brother. X, right? So this is a simple linear equation. You can fit a line where B, A is the slope, B is the intercept, right? Instead of 1x, we just have px's, that's it. So the one above is simply an expansion of what looks like a straight line. And we have many, many slope values here. So you can think of this value here as the intercept, and then each of these values is the slope. Every single beta here is a slope for a different feature. Right? And a slope is also a way of thinking about importance. Beta can be a positive value or a negative value. If it's a high positive value, then very high values of that particular feature is very indicative of the target variable. If it's a large negative value, then very small values of x is very indicative of the target variable. But if beta, any of the betas is very close to 0, then it means that that particular feature, or in this case, that particular gene, is not so important in determining the outcome variable. All right. So I am going to, these values are also called the parameters of the model. Right? Parameters of the model. These beta values, right? So this one here, this one here, this one here, this one here. Okay, these are the parameters of the model. What we can do is to figure out, once you have what the model is supposed to do is to take this data set. We know y, which is a particular tissue. And let's say, y in this case is, let's say the sample comes from, brain, adipose, liver, lung, and so on. We are going to do something called binary classification. Binary classification. Focusing in on a single tissue, because of which we are going to say y is either 0 or 1. By picking a favorite tissue of interest. So let's say brain, we're going to say every sample that comes from brain, I'm going to make the y1, and every sample that doesn't come from brain, I'm going to make the y0. Right? So y only takes 1 or 0 because you've chosen a tissue. And then the model is supposed to predict what are the values of beta, so that when you combine them with the expression levels of all the genes in a particular sample, you can predict whether the sample comes from brain or not, 1 or 0. We can also quantify, once the model has figured out what an appropriate values of betas can be, you can also quantify how much error the model is making by comparing the predicted value of beta, which is y hat, to the true value, predicted value of the outcome variable to the true value of the outcome variable y. Okay, because for every sample, we know whether the sample came from brain or not because we have this data, which is the ground truth here, right? Which is the ground truth here. But we can also ask the model, what does it think the sample is, whether it comes from brain or not. You can compare these two and then figure out how much of an error the model is making at any given point. This is called the error, okay, that the model is making. Now, the model is also tuning these parameters, beta 0, 1, 2, and 3, and 4, so that it can reduce the error as much as possible. However, when that happens, typically, if there are many, features that are part of the problem, you can end up training very, very complex models that gives us very low error or very high accuracy. Okay? a complex model is when many of these betas are not close to zero. They are either very large positive values or very large negative values. Okay. And many of you would have heard of this idea called the Occam's razor, right? Typically, what we want to do is to not go for a very, very complex model to make predictions about the future or generate hypotheses. Instead, what you want to do is to find the simplest model that can still give us really good, accurate predictions. So therefore, you can think of all the beta values together in some way as the complexity of the model. If many of them happen to be very large values, positive or negative, then the model is very complex. So another way to define complexity is to say, I am going to define beta j for all j. Okay? And this is my complexity. You see that this is an absolute value. If beta is very high positive value or very low negative value, you'll end up with still a high value. So if many of the betas are very large, this quantity is going to be very large. Now, these two are opposing forces, right? Error and uncertainty, because you can increase complexity and decrease error very easily. Right? So what these optimization algorithms that train machine learning models do is to find out the best set of beta that can reduce both. It can keep the error low and keep the complexity low, right? So, and one of the ways in which we do this is to set up a penalty parameter, which we as the user have to define. And then we say that if the penalty parameter is very high, then it becomes very costly for the algorithm to build complex models. It becomes very costly for the model to pick very high or very low beta values. So it will force the model to make most of the beta values close to zero. Right? So we set a penalty. This penalty parameter is something that is provided by the user and is an example of a hyperparameter. Right? So remember, these are parameters that the underlying model learns, and the hyperparameter is something that we need to provide as a user. We need to essentially say, how much do you want to penalize the complexity of the model? All right. Finally, I want to talk about model evaluation, and this is the last topic that I'm going to talk about using my iPad, and then we're going to switch over to the code part. Okay. Now, let's just think about training and validation alone, and we'll worry about testing later, right? So here, I have tried to draw a part of the data set, and this is the training set, okay? The training set. And let's say this one here is the validation set. Remember, both of them are essentially small parts of the original data set that we started with, all right? So what we're going to do is to take the training set, okay, build a model which is going to predict Y from X, right? And apply that model to the validation set. Once you take this, once you apply this function to the values in the validation set, what you can do is to get predictions. This is Y hat. Okay. For each sample here. So remember that there are many validation samples here. Sample 1, sample 2, sample 3, and so on. And for each one of them, by applying the model that you trained based on the training data, you can get a prediction, right? So which means that you're going to get a prediction of sample 1, sample 2, sample 3, and so on. However, for each of these samples, we also know what the ground truth is. Because it came from our original data set, we already know what the target variable is, or whether the sample came from a particular tissue or not. So what you can do is to turn these two together into a table like what I've drawn on the right. Okay. Typically, the model that I'm talking about is one way to think about this linear model is called the logistic regression. And it outputs the probability that a particular sample, let's say, comes from brain. Okay. So you can take all those probabilities for each of your validation samples and then put them together as a table like this, and then rank them from the highest probability to the lowest probability. The highest one here is 0.99, 0.95, 0.91, and so on. And on the right, I know whether the sample really came from brain or not. And I'm marking that with a positive or a negative. If it's positive, it did come from the brain. Negative, it didn't come from the brain. Right? So I do this. Now, what I can do is to get a threshold here, let's say somewhere here, draw a threshold and basically say that let's say I predicted that all of these are from the brain and everything below is not from the brain. Let's say that's my prediction. I can compare it to the ground truth, which is all this here, right? Which is all this here. I can compare it to the ground truth and figure out how well my model performed. So just to bring this idea home, let's say this is reality or ground truth. And let's say this is prediction from the model. Right? And let's say in reality, we are talking about samples that are really from brain, those that are not from brain. And let's say based on the model, we predict whether the sample is from the brain or not from the brain. Okay. If this is true, hopefully the following statements make sense to you. If the model predicted the sample to be from the brain, and in reality it is from the brain, it is called a true positive. Okay. If the model thinks that the sample is from the brain, but it is not, it is a false positive. Okay. And hopefully the other two values also make sense to you. Right? The model predicts something as not from the brain, but it is really from the brain. It's a false negative. And of course, the last one, where the model and the reality agree that the sample is not from the brain, it's a true negative. Right? The goal of any algorithm is to make sure that the true positives and the true negatives are as high as possible, and the false positives and false negatives are as low as possible, right? In general. Okay. So there are many performance metrics that take these values and then combine them into a single summary and then help us interpret how good the model is. Okay. In the interest of time, I'm not going to go over these things, but some of the things that you should start looking up are things like precision. What fraction of the samples predicted by the model are correct? That's what precision is. Recall. What fraction of the samples from the brain did the model predict correctly? Okay, that's recall, and so on. Okay. And then there are things like sensitivity, specificity, and so on. There are many metrics like this. Okay. One more thing to remember, note here, which I'm not going to go into detail, is that remember I drew a horizontal line and then said that this is the probability cutoff that I'm going to use, and say that everything above that I'm going to predict as from brain, everything below that not brain, right? But you can choose any threshold you want. So what typically happens is that you can choose every threshold possible and calculate one of these metrics and draw something called performance curves, where you can plot the metric as you change the threshold and look at that curve to make sense of what is happening underneath. Okay? If the different curves have different shapes that correspond to good performance and different shapes that correspond to not so good random performance. And then you can use that curve to basically interpret how good the model is, right? Okay, let me pause here and then I'll take a couple of questions before I go and show you some code to actually do this in practice.
There's currently no questions in the chat.
Okay. Either this is incredibly clear or I've lost all of you already. Okay. Can folks give me a thumbs up if all this sounds reasonable to you?
Everyone in the chat box is saying you're doing a great job.
Correct. Okay, awesome. Thank you. All right, so let me switch over from my, tablet and then go over to the code, okay? Stop broadcasting, and I'm going to go over to the code. How are folks doing in terms of installation? Is it working for you? Are you able to install tools? I'm sorry if you're not able to, if you've not been able to install these things. Sometimes, there are going to be clashes with versions of packages and versions of R and versions of RStudio. This is the bane of data scientists, okay, or anyone who analyzes data. So I'm sorry if it didn't work for you. This happens in the lives of real researchers all the time. So please come back and try again with the video, hopefully helping you along. Okay. Okay, so Pamela has a question. So she has, does supervised learning require a training set versus an unsupervised learning? The only difference between supervised and unsupervised is that both require a data set, but in unsupervised learning, you don't need any other external information about the samples. So you can take a gene expression data set and do unsupervised learning. Now, supervised learning, the only other piece that you need is external information about every single sample. So if the samples are houses, you need something like the price of the house that you want to predict. Or if it's biological samples, you need to, if you want to predict the disease status of that sample, that disease status is the external variable that you need. Hopefully I answered your question, but if not, I'm happy to chat afterwards. All right. Okay, folks. So hopefully you can see my screen here. And this is the R notebook that I prepared for all of you, okay? And I've split my screen. Oh, okay. So Ernesto is asking, what is the require package matrix? Require package matrix. Is there a matrix package that is required? I'm not really sure. Have I used it right here? It seems to be complaining about that. Oh, okay. I'm sorry. You can, in the chat, can you post, at what stage it's complaining, and then I can try to troubleshoot, but I will keep going with, how this notebook is organized. So I'm going to show you how this notebook is organized so that even if we run out of time, you can all go back and, try this on your own. There are 5 sections. You can see the sections at the top right, especially if you open the HTML in one of your favorite browsers, right? Brave, Chrome, whatever it is. You should be able to click the HTML file and should open. And what you're seeing on the right on my screen should be the one that you see in the browser, right? So it has all the code and explanations of the example that I'm going to work out today. Okay. It begins with installing and loading the packages. And the package that we are going to use today is called Tidy Models. And it's a really new, and here's the web page, okay? It's called tidymodels.org. And it's amazing because up to this point, the package and the software infrastructure for doing machine learning was really, really good in the Python environment, but not so much in the R environment. Because in the R environment, many researchers are basically developing different machine learning algorithms and packages that were not necessarily talking to each other, and if they were not doing so in a very harmonized way. So Tidy Models is a community effort to sort of harmonize all these things so that you can use the same, very similar ways of data, representing data, processing data, and use any machine learning algorithm without having to completely switch out the way in which you write code. So you can write code very similarly, independent of what machine learning algorithm you want to use. You can use a logistic regression or a support vector machine, random forest, it doesn't matter, right? So this is a great work done by a bunch of folks in the community, including Julia Silge. So you should check this out. And we're going to use this package. If you install Tidy Models, it already comes with many other packages that are sort of, it's like a super package. It has R sample, parsnip, yardstick, tune, recipes, and so forth. So we're going to use all that stuff. Now, at the beginning, so here we're going to load the library, Tidy Models, and also load the library Tidyverse, which is for data wrangling, right? It's great for data wrangling and data visualization. So hopefully folks who took some of the other sessions in this data week came across, things like dplyr or ggplot for visualization. So all that is packaged inside tidyverse. Okay, so we're going to use that. And then the last package is called glmnet, which contains the algorithm for training a logistic regression model. It has algorithms for many other linear models. Okay. All right. Now, if you are able to execute this on your laptop, I strongly suggest starting here. Basically, once you open this notebook in RStudio, you can select the commands that you want. And then if you hit the play button on the top right of every code chunk, it will run all the commands in that code chunk. Okay. So for example, if I hit this, it's going to run and then produce the outputs. Okay. So you can see the output here. All right. The next thing here is the command to read the data file. The data file is here. Okay. And I'm going to read this. I'm going to use this function called read.dlim, read_dlim, and load this file here. It's going to take a while. All right, there you go. So immediately, it's telling you here that it has 8435 rows and 3688 columns. Okay. Here, the rows represent biological samples. There are more than 8,400 biological samples, which are all the rows. And from each, I have essentially taken this data set and somehow thrown a large number of genes because we want to load this hopefully in a laptop or a desktop, and only kept about 3,600 genes. So there are 3,600 columns, and every value here is the expression level of a particular gene in the column in a particular sample in the row. Okay, so that's the expression level. So let's print this and see how the data set really looks like. Okay. All right. So here's how the data set looks. The first column tells you which tissue the sample came from. And then every subsequent column is the name of a gene and the expression level of that gene in that sample. Right. So for instance, this means that this is the expression level of this particular gene in a sample that came from adipose tissue. That's what this means. Right. And then there are 3,688 columns here, which we are not going to show. We are going to use dplyr chops to quickly figure out how many samples are there from these various tissues. Okay. And here, this table tells us that of these, you can take all these, 8,400 odd samples and split them. They belong to 5 different tissues. And these are the number of samples from each tissue. And this is the proportion, all right, proportion of samples out of those total that come from each of these tissues, right? Going to skip this part in the interest of time. And now we are going to start setting up the machine learning model. Right? Remember, I told you that in this example, in this session alone, we are only concerned about a binary classification problem, which means that we are going to classify whether a sample belongs to a particular tissue or not. But there are 5 tissues here. So we have to pick the tissue of interest for us. So I'm going to say, the tissue of interest for me is esophagus, right? So I'm going to pick that. And I'm going to store that in this variable called pos tissue. Right? And what I'm essentially going to do is to go to the data set. And you remember this column called tissue, right? And I'm going to modify it so that whenever the sample comes from esophagus, I'm going to replace it with the word correct. And whenever the sample is not from esophagus, I'm going to replace it with the word not correct, right? Or incorrect. That is all is happening here. Okay. Once I have made that modification, you can see how the data has changed. Remember the previous table under tissue, you had 5 different tissues. Now it is just correct or incorrect. Correct corresponds to esophagus, incorrect corresponds to non-esophagus. Okay. And this is the proportion. Now, one of the really important things to note in any machine learning model is really have a good grasp of how many positive examples and how many negative examples are there in your data set. In this case, there are 1,400 positive examples and almost 7,000 negative examples. So this is a case where the classes are highly imbalanced. You have very few positives and way more negatives, right? And this is a very common setting in many biomedical or biological settings, where the number of things that we care about or want to really classify are very small compared to the negative examples that we can collect. So for instance, if you want to take X-ray images and classify them based on whether the patient has a particular cancer or not, you're going to have way more X-rays where the patient has a particular disease. And it's way easier to collect a large number of images where the individual does not have the particular cancer, right? So you're always going to have this huge imbalance. So we're going to keep this in mind in deciding what to do in the next steps, right? This is our full training set, full data set. Okay. All right. Now we're going to move into the data splitting phase. Remember, we can't just take this entire data set and train a model because we can't do anything after that. So what we want to do is to take this data set and split this into training, validation, and testing, so that we can take the training data set, train a bunch of the same model in a bunch of different settings, test them on the validation set, figure out which is the best model setting, and then finally take that best model and then apply this to the test set, right? So we're going to do this. So we're going to do data splitting. In this data splitting, you should notice something important here. There is a parameter called strata. Okay. And that strata is set to tissue. I have written explanations about what these, functions are in the text. You should try to read this after the session. But here is a question for you. Can someone tell me what the strata is or what the stratification is? Your best guess.
Maybe you're ensuring like you don't want to lose all your like the tissue of interest, the correct into the trainings and have none. So you're making sure that they are represented in all three data sets.
Super. Yeah, it's exactly that. So in our data set, we only have 17% of the samples are come from esophagus, and the remaining samples are all non-esophagus. So if you want to make sure that this proportion, we want to make sure that even when you do validation or testing, we need to make sure that if we can try, we should trust our evaluation or how good the model is. We need to make sure that the validation and the test set also have very similar disproportionate, distribution of esophagus, non-esophagus, so that we can represent reality as much as possible. So the strata thing tells us that you should not only randomly split your data set, but you should randomly split so that the proportions of positive and negatives is the same across training, validation, and testing, right? Okay, so now here is the training and validation together. I'm going to call this other. Okay. Not printing. If in your notebooks, these will print tables and they will show you that the proportion of positive and negative is the same in these two splits, right? Now, here is where we're going to take the non-test samples and split them into training and validation, right? So there is a validation split function here. And again, there is a strata here. And this proportion 80 basically says that I'm going to take the non-test samples and then keep 80% for training and then 20% for validation. That's what this 0.8 means. All right. Now we have split the data set into training, validation, and testing. I think we had ended up with 60%, 20%, and 20%. All right. Now we are going to build our machine learning model. This is the logistic regression model that I talked about. Okay. We are going to use tidy models to do this completely, right? And in tidy models, a really good thing is called, there is a part of tidy models is a package called parsnip that allows you to specify a model, okay? Completely independent of your data set. So in this case, I'm going to specify the model that I want to build. Here, I say I'm going to build a logistic regression model. And I'm going to build this model from this package called GLMNet. GLMNet has the optimization algorithm to build this logistic regression model. So if you want to build, let's say, a random forest, you will specify a random forest. And then in the set engine, you will specify which package do you want to borrow this random forest from. That's the second command there. And within logistic regression, I also told you there are these hyperparameters, right? So I'm specifying one hyperparameter here, which is called the penalty. The penalty tells you, we tell the algorithm how much we're going to penalize the complexity of the model. So if the penalty is very high, we're going to try to make the model really simple. But if the penalty is very low, the model is going to become very complex. And this is something that we provide. Another really nice aspect about tidy models is this idea called recipes. So what one can do is to build a recipe that we use over and over. First, we use this on the training data, then we use this in the validation data, and again, we are going to use this in the test data, right? So the recipe is very simple. We're going to predict tissue as a function of the expression data here. All right, so that's the prediction. And then there are two other steps here. These recipes are also very good for doing data pre-processing, which means that if you want to adjust the data in some way before you build a model, you can build those steps into the recipe. Okay. These two, I just added these two steps. You can do this, you can do way more complex things here. The first step in this recipe says that if there is any gene that has the same value over and over for all the samples, it's going to be a gene that's meaningless, right? So we're going to remove that gene. So any gene that has zero variance is going to be removed. And then we are also going to normalize the values of all the genes so that values across genes are comparable to each other. Because we don't want to bias the model, because there are some genes that are going to be generally have very high expression, irrespective of the tissue. Right? So we don't want to bias the sample, bias the model towards such genes. So we're going to do normalization. And finally, we're going to build a workflow. The workflow is going to combine the model and the recipe together. The workflow is, I'm going to start a workflow, add the model that I first described. First, it's a logistic regression model from GLMNet. And then I'm going to add the recipe that I just described here, how to prepare the data to provide this to the model. And then the next step here is for us as the user to provide all these tuning penalty parameters that we want the model to try. Okay, these are the slightly different model settings. Okay. In this case, I'm going to try values from 10 power minus 4 to 0.1, 10 power minus 1, okay, and about 10 values from this low value to the high value. Then train all that. Once we have figured out the penalty values, what the workflow allows us to run this model that we specified, run this recipe using this grid of parameters, and then store all the results in this particular variable here. So run the workflow across all the parameters. And it's also going to do one more thing. It is going to, for each model parameter setting, it's going to record the performance metric for that particular model setting. The performance metric that I'm going to show here is the area under the receiver operator characteristic curve. It's called the area under the ROC curve. And I don't have time to explain this, but the area under the ROC curve has a nice, you can interpret this in the following way, right? So if if you somehow play chess, for example, you begin the game by taking a black pawn and a white pawn, sort of hiding it, switching it behind your hand and showing the opponent and asking them to pick which side, right? So the area under the ROC curve is also like that. If you randomly show a positive example and a negative example to the algorithm, the area under the ROC curve is the probability that it correctly picks the sample from the positive example with a higher probability. That's it. So it has a nice interpretation, so we're going to calculate it. And let's run this model. So we have not done anything up to this point. once you run this model, okay, it has stored the area under the ROC curve for every model setting, which is slightly different penalty value. Okay. So now we're going to go and then plot. And what we are plotting here is the performance of the model for various model settings. Essentially, we provided 10 different penalty values, which are along the x-axis. Every point here is the performance of the model for that particular value of penalty. So here it turns out that hopefully you will agree, at least with the in conclusion, that if you make the model less and less complex, at some point the model totally breaks and becomes random. And the AUROC of 0.5 corresponds to random performance. So you can't make the model totally not complex. Right? You need some level of complexity, but not too much also, right? So because even if you have slightly less complex models, you can still get good performance, right? So now is your chance to pick the best penalty parameter to go forward with, okay? Now, here is something for you to think about, right? I can easily pick the first penalty parameter and just go forward with it. But there is a problem, right? Because if I pick the first one, it is the most complex model. So you're better off keep going to the right until the point the model doesn't lose the performance anymore, but still is the least complex model as possible. So perhaps this point here, which is the 6th value that we tried, is actually not bad, because beyond that, if you increase the penalty even more, the performance reduces. But up to this point, the performance is almost as good as a really complex model, right? So you can pick this. So what I'm going to show you here is essentially to pick the model that corresponds to a really good performance, but as least complex as possible. And you can even plot the area, the ROC curve itself from which we calculated the area. Unfortunately, within this 1 hour, I have not had a chance to tell you what this curve is or how to interpret it. But if you look at this notebook that I've provided you, there are links that point you to Wikipedia pages that explain what this curve is. So typically, a really hand-wavy explanation is that this dotted line here, if the curve followed this dotted line, it would have meant that the algorithm that we trained, or the model that we trained, just does a random classification. If the curve is towards the top left, the more it is towards the top left, the better the prediction performance is. Okay. All right. So I'm going to stop here. There is a few more things in the notebook here, because it's going to tell you about why it is important to not just look at the ROC curve, but also to look at the precision recall curve, because remember that our problem is highly biased, right? We have very few positive examples and many more negative examples. And the ROC curve will actually not give us a good picture because it is not sensitive at all to this imbalance. So you might end up with a very good ROC curve, but still have very poor performance on the tissue that we care about. Because ROC will be high even if you make many negative predictions correctly. But many times what we care about is making positive predictions correctly. Right? So that's where it's important to go look at other measures like precision and recall. Right? Okay, this was a hyper speed, intro to machine learning, where I had to try to, squeeze in a little bit of, underlying ideas and also code. But I'm happy to take any questions for folks who want to hang on. Otherwise, thanks for joining.
I do have a quick question.
Yes.
So is this ROC curve based on your training model, or did you include the validation set?
Excellent. So the ROC curve is based on, let's go to this curve here. The ROC, every single ROC value here is taking the model that is trained on the training set for a particular penalty value and applying this to the validation set and calculating the area under the curve. And that is this value here.
Okay.
Then I change the penalty a little bit, train the model again, apply this on the validation, I get the next point. So every single point is testing on the validation set.
Okay, perfect. Thank you.
Thanks for the question.
I think I'm missing a step because right after the ROC curve, I get an error attempt to use zero length variable name. Did you set the penalty at some point, or what am I missing?
Oh, it is possible. So here, this line here, here's where I set the penalties. There are 10 penalty values that go
Great,
from 10
great. Gotcha. Okay.
Sorry, I skipped a bunch during execution just in interest of time.
Yeah. Okay. Well, I'll play with that later.
Okay. Sounds good.
Any other lingering questions? Just a reminder, please fill out the attendance so that you're entered into our raffle. Follow us on LinkedIn or Twitter for updates on when we post the videos. And other than that, thank you for joining us. Thank you, Arjun. This was like really awesome. I really enjoyed your presentation, as I'm sure everyone else did. So thank you so much.
Thank you. It was great.
Thanks, everyone. Thanks, Lala.
Good night.
Bye.